Okay, so this is the projectile motion experiment. So in this experiment, our goal is to measure the horizontal range as a ball rolls off a ramp, flies through the air, and lands on the floor. So our goal is to measure the horizontal range and compare it to a predicted value that we were going to get. Okay, so when we analyze these types of problems, we have to look at each component separately, the y component and the x component. So let's look at the x component, our horizontal component, first. So as the ball flies through the air, if we ignore air resistance, we can say that there is no acceleration in the x direction, since there's no other forces acting in that direction. So we're going to assume that it's moving at constant velocity in our horizontal direction the entire time of flight. Okay, so we can simply write that as change in distance over change in time. Now I'm going to change that to the term to r just to represent range. So that's going to be our predicted range over time. And I dropped the delta just for ease of doing algebra. Okay, so we can solve that. And we have our predicted range is going to be equal to our horizontal velocity times the time of flight. That's the time the ball leaves the ramp to when it hits the ground. Okay, so we don't know what this time is. So we're going to we need another equation to figure this out. Our horizontal velocity we can figure out using a gate, a photo gate. So we have a photo gate, and the ball is going to pass through the gate. Okay, so our computer can measure the time it takes the ball to enter the gate to the time it takes to leave the gate, which will be a pretty small time. Okay, and it's traveling one ball diameter in that time. So distance over time, we can say our horizontal velocity is the diameter of the ball divided by the gate time that the computer provides us from our photo gate. Okay, so we can measure our horizontal velocity, but we need to figure out time. So now we look at our y component, our vertical component, y. So we know in the y direction gravity is acting, and it's a constant force, therefore it's a constant acceleration, ignoring the force of air resistance. Okay, so that means our kinematic equations apply, or that is our uniform acceleration equations apply. So we're going to choose this equation, which says our height, the vertical distance that the ball moves, is equal to its initial vertical velocity times t, that's the same time we had up there, plus 1/2 gt squared, where g is the acceleration of gravity, 9.81 meters per second squared. And again, this is the same t time of flight. So we want to solve this equation for t and then substitute it into our equation we had above to find r predicted. All right, but let's try to simplify it first. Our initial vertical velocity. So what is the initial vertical velocity if the ball leaves the ramp horizontally, perfectly horizontally? Okay, so hopefully the answer to that should be straightforward, and it should help you to simplify this equation to solve for t. Okay, so we'll solve that for t, plug it into this equation, and as you're assigned to do in your lab report under the theory section, you can show, after you show all the algebra, that you'll get a predicted range of this. So this is your horizontal velocity as we showed how to calculate before. And this is your height, which we called y before, but I guess we can also call it h to represent height. And acceleration of gravity, 9.81 meters per second squared. Okay, so now we have a predicted range that we can compare to measured range, which we will physically measure with the meter stick. Okay, so let's look at the experiment. Okay, so we have this setup. We have our ramp. We have our photo gate. We have our ball that we're going to move, and as I mentioned, it's for the horizontal velocity. It's going to measure the time it takes from the ball to enter to leave the gate. So just as short amount of time as the ball rolls down the ramp. So we can measure the ball diameter using our caliper. Okay. And we should be able to look at the data there for that. We can see roughly just it's going to be around between 4.3 and 4.4 centimeters. And we use our tick marks on our caliper to get our exact decimals. Okay? So we also have to measure the height. So we can simply use the meter stick to measure from our ramp to the ground. Alright? And in addition to that, we have to, when we measure our range with the meter stick, we need to find the point directly on the ground, directly underneath the end of the ramp. So we can use a plumb line to do that. So we can put that here at the end of the ramp, and it gets the point directly beneath the end of the ramp. Okay, I have that marked down there. Alright, so once you do that, you can measure range. Right, so let's do a trial. So we have this piece of white paper taped to the floor, and I have this piece of black carbon paper, which I'm going to place over this white paper with the dark side facing down. And we're going to go ahead and do a trial. So I'm going to hit collect on this. And we have to select a point on the ramp that we're going to release the ball from for every trial, the same point. Okay? Alright. So we got some time. And as we saw it, we knew it was going to be a small time value. Now, if we look at what this carbon paper did, the ball landed on it, and it made a mark. So now we can measure our range. We can use the meter stick to measure from this point to our mark. And that would be your measured range value. So that would be a direct value. And your gate time, as we said, we'll use the ball diameter divided by the gate time to get your horizontal velocity. And then we use your horizontal velocity and the measured height to get your predicted range. Okay? So for each child, you're going to have a measured range and you're going to calculate a predicted range. And you're going to do several trials. The more trials we get, the better, of course. Oops, there we go. And we're going to, once we collect all of our trials, you're going to calculate your speed and predicted range. And then you're going to calculate your average, standard deviation, and standard deviation of the mean for both predicted range and measured range. Okay? And then you have questions to answer, and we're going to compare our average predicted range to our averaged measured range using the standard deviation of the means. Okay, remember it's your average plus or minus the standard deviation of the mean. And that should be the extent of the projectile motion experiment. Thank you.